The discovery of the electron majorly happened in the early 20th century. There were many scientists, chemists, and physicists who contributed to the knowledge that we now have and the understanding of the atomic model and the motion of electricity. It has since been utilized in countless technologies and has been used so prevalently in the way we live that should we take away our understanding, life as we know it would change completely. The father of the electron is the nickname of J.J. Thomson, who's a British physicist whose experiments were crucial in the understanding the particle composition of atoms. Through his experimentations, he also discovered that electrons have a much smaller mass than hydrogen atoms, which at the time was considered to be the smallest known particle. Most experimentations were based off of this conclusion and did yield some incorrect understanding of how matter flows and works in the world. So, some history on J.J. Thomson. He studied at what is now the University of Manchester. He was admitted when he was 14 years old, and at that time he began his experimentation. As he studied under some of the professors there, he eventually moved on to Trinity College in 1880, where he received his Bachelor and Masters of Arts degrees in mathematics. He was a very well-known mathematician, and he was high esteemed. He then became a professor at the University of Cambridge, where he stayed for a majority of his career. This did surprise a lot of his peers, given his background in mathematics, but he was known to be a very smart man, considered a genius, and in 1937 he did end up winning the Nobel Prize for proving wave-like properties of electrons. This later would become very important in our understanding of the way electrons move, and would then start the discovery of quantum physics. Some other scientists that were very crucial and in our understanding of the electron motion also include Jean Perrin, who is a French physicist who hypothesized that each atom had a positively charged nucleus, but he never pursued the theory. In his experimentation, he developed the understanding that matter contains a discontinuous structure, and he developed theoretical explanations for the random motion of atoms when suspended in a medium. He did a lot of experimental work that also was aligned with that of Albert Einstein's predictions under the same topic. His understanding of nuclear physics was ahead of much of the other scientists of his time, and he was among the first to show that cathode rays contained an electric charge. A more in-depth explanation of cathode rays will be given later in this video, but this experiment did involve two wires located at either end of a vacuum. The vacuum that Jean Perrin used was Faraday's cylinder, and he would project a strong voltage between the two wires. And from his experimentation, he looked both into positive and negative charges that occurred in a motion of electricity. He reversed the flow of electrons and was able to change the charge with which from a negative to a positive voltage change within that vacuum. Another scientist is Sir William Crookes, who's an English chemist. He invented what is known as the Crookes tube, which he created in 1875. He was the pioneer of vacuum tubes, which was crucial to his research in spectroscopy, or the interaction of electromagnetic forces and their interaction with matter. His research and studies mostly focused on gases, and he found that his glass vacuum container was capable of carrying electricity. And when he shot 10,000 volts of electricity in the vacuum, the tube would become fluorescent. His conclusion from his experiments were that energy was typically traveled in straight lines and collided with anything in its path. At this point, the electron was not yet considered discovered and was just put under the general umbrella of electricity and energy. Emil Weishart was a German physicist who was one of the first to theorize that electrons have a very small mass to charge ratio. His work also utilized cathode rays, and in his experimentation, he became one of the first to discover that cathode rays are particle streams. His experimentation did show much of the same as Thomson's discoveries, and he likely could have been considered the father of the electron. However, as he was working on his experiments and discoveries, he stopped short of theorizing of electron particles, and because of that, he's not credited with their discovery. So some more explanation on cathode rays and kind of the operation of the experiment. They are named cathode rays because they are emitted by a negative electrode, also known as the cathode, in a vacuum tube. And to release electrons into the tube, they must first be detached from atoms in the cathode. In the early experimental called Cathode vacuum tubes, in which the cathode rays were discovered, this goes back to William Crookes and his tube invention. It was done using a high electrical potential of many thousands of volts between the anode and the cathode, and this ionized any gas remaining in the tube. Any positive ions were then accelerated by an electric field towards the cathode, and when they knocked electrons out of the surface, these were then what are considered the cathode rays. Modern vacuum tubes are created from wire filaments, which are heated and by a separate electric current passing through it, and the heat provides energy for electrons to escape from the surface of the filaments into the vacuumed space in the tube. Since electrons have negative charges, they are repelled by the negative cathode and attracted to the positive anode. They do travel in parallel lines through the empty tube since there is no matter within the tube to disrupt their path, and the voltage is applied between the electrodes. These accelerate low mass particles to very high velocities, and these rays are also invisible. Crookes is the first who did discover their presence because of the way they did cause the glow or the fluorescence within the tube. And so that was majorly what gave way to an understanding of their physical presence. And researchers also noticed that objects placed within the tube would cast a shadow. So with this came the realization that these electric particles do travel in straight lines, and if they do, and that they are stopped by physical objects in the way. When electrons hit the back of the tube and they make their way to the anode or the other wire in the tube, they then travel through to power supply and back to the cathode wire. And so this is what created then the electric current throughout the tube. The current in a beam of cathode rays through a vacuum can be controlled by passing it through a metal screen of wires in a grid. And when these small voltages are applied, the electric field deflects some of the electrons and prevents them from reaching the anode on the other side of the tube. The amount of current that gets through depends on the voltage of the grid. And so a small voltage on the grid can be made to control a much larger voltage on the atom, and this is the principle that was used in vacuum tubes to amplify electric signals. These vacuum tubes were developed in the early 1900s, between about 1907 and 1914, and became one of the first electronic devices that could amplify, and is used in radios and televisions and other forms of transmitters. So a lot of these high beams of cathode rays, they were manipulated in experiments by electric fields and magnetic fields. And so a lot of these experiments did involve the creation of different fields in which these electrons would pass through. So J.J. Thomson, who is pictured on the right, his experiments his goal was to bend cathode rays within these tubes. His theory was that if he managed to bend these rays out of the straight lines in which they traveled, that the charge would theoretically be able to be separated from the rays, and that the charge was independent of the particles present. He did find that the rays did in fact curve in an electric field, but only in a vacuum chamber. And as previously mentioned, if any gas still remained in the tube, then it would transform into a conductor and it would interfere with the experiment, because the particles would no longer be traveling in a straight line and would then be interrupted by these particles that still remain in the chamber. So through this experiment, he did get measurements of energy for electrons by measuring voltages and currents, and he was also able to find the mass of the electron. So some of Thomson's conclusions from his experiments included that cathode rays are comprised of charged particles. Since the word electron had not yet been coined to name the negative particles, he called them corpuscles. And so his other hypotheses were that corpuscles are part of an atom, and that corpuscles are the only constituents of an atom. And so on the right, we can see kind of the development of atomic theory and different models. John Dalton assumed an atom was just one continuous mass, and that it was just a solid piece of mass. Thomson envisioned it as a solid particle that contained even smaller particles that were just floating around that were negatively charged. Rutherford and Bohr then came up with more accurate models where both positive and negative charges are present in the atom, and Schrödinger then has the theory of the electron cloud in that structure. One of Thomson's most significant conclusions from his experiments were that electrons would occasionally behave as waves and not always as particles. This led to the development of quantum theory, and until that was developed, we still did not have a great understanding of the behavior of atoms. Ernest Rutherford was a nuclear physicist who developed the idea and more accurate atomic model that is currently taught in elementary levels of chemistry and physics. And his model displayed both positively and negatively charged particles and atoms, and he did have one of the most accurate models of his time. This was done when he asked some of his co-workers and peers as he was working to discover the nuclear nature of atoms, he shot alpha particles at atoms and looked for any deflection of these particles. In Thomson's model, because the electron particles were so small, these alpha particles would be able to pass straight through the atom and hit the a paper that was, or gold leaf that was at the, was behind the atoms. Um, and they were looking for like very high deflection angles. And they did not expect anything to really come of it because it was not anything that aligned with any theories of that time. But they did find that these super high deflection angles did occur. They were relatively rare, but they did find alpha particles that would have a very high deflection angle. And in one of his last lectures, he said, quote, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." End quote. And so Rutherford's interpretation of this data led him to propose the idea of a nucleus, which is a very small charged region containing much of the atom's mass. So Rutherford was one of Thomson's biggest critics of the atomic model, which did lead him to this further experimentation. And so um, in his criticism, J.J. Thomson's model was disproved, and his third hypothesis that atoms were only made up of electrons was also disproved. So Thomson's first two hypotheses were in fact considered to be correct by many of his peers, and that atoms do contain negatively charged particles, and that those particles are a part of the atom, but they do not solely make up the atom. And that is a brief history on the discovery of the electron, and here are some of the resources used. Thank you for listening.